Welcome to the Grid Mod Pod, brought to you by AEIC. In this podcast, you'll hear from the utility industry's top operations leaders on how their companies are working to modernize and improve our ever-evolving power grid. Thanks for joining us.
Welcome to the Grid Mod Podcast, where we delve into the cutting-edge technologies and strategies that are reshaping the energy landscape. Today, we're thrilled to have Steve Tyler, the manager of DVI Solutions at Dominion Energy, really join us for an insightful conversation about really all things distributed energy resources and their interaction with the electrical grid. So welcome, Steve. Thanks for joining us today. Why don't you take a little bit of time and introduce yourself to our audience?
My name is Steve Tyler. I'm with DVI. DVI is Dominion Voltage Incorporated. It's actually a technology firm within the umbrella of Dominion Energy. So it's a little bit different that we're a software company that sells software to utilities across North America, even though we're part of Dominion Energy.
So we're going to just jump right in and really, could you shed light on how DERs acting like variable loads are affecting the distribution grid? I'll give you a softball.
Well, yeah, DERs, whether it be solar panels or other forms of distributed energy, storage, loads, et cetera, are introducing a lot of fluctuations on our grid. So it's fluctuating load as clouds come and go, as EV chargers come on and go off. So the fluctuations are some of the big impacts. Also for as a generation source, they're not always there. They're not always there when you need them. So what we've seen is that you kind of need a tool that can help manage these resources. It used to be that distribution operators had to worry about storms coming and going. Now just clouds coming and going can have a similar detrimental effect on the grid.
Do you have any examples, or maybe like how do these challenges manifest during that peak demand time? For instance, what's a application that you see kind of privy to some of your engagements? And I like to really share just anecdotes because like throughout the conversations of the Grid Mod Pod is, I think one, you have to hear it more than once. And, when we talk about distributed energy resources, I guess I'll just remind the audience is, the industry is facing new technologies. What are those new technologies? It's devices that are being attached or connected to where our customers predominantly have been in all forms. So as you just said, the solar, et cetera, can go up and down. What are some opportunities when you do have the peak demand times that we can use these assets to help, play those role as like an asset to the grid instead of, being a detriment?
That's a great question. So we have seen an increasing number of severe situations. Duke had some, Texas has had some, where what used to be a rotating blackout has become more prevalent. So that was a major focus at the Seagray conference this year around how to deal with and mitigate these rotating blackouts. Historically, there was emergency voltage reduction in the term of brownouts, but it was really done kind of in the blind, where you turned down the voltage at the substation and you didn't know exactly what was happening at the customer level. And so that's one of the areas where distributed resources are great when they're adding power to the system, but they're not always there when you need them. So having the ability to interact with that and cover for the loss of distributed resources, maybe during a time when you need it and are losing traditional resources, is something where voltage management can come in and play.
And I think, one of those devices that got a bad rap really in 2009 and beyond, the smart meter, which, it is what it is, maybe a buzzword, but, can you discuss how the deployment of these smart meters, or aka AMI, which is another term we use, advanced metering infrastructure, really the deployment of that nationwide and how they extend and really provide maybe the keystone to really tap into, all of these DERs that we speak of.
That is a very key technology that has really provided a benefit beyond maybe what it was originally envisioned for. I think the first idea of a smart meter was something that eliminated the need to go read the meter door to door, which was a major advantage. You didn't need to send someone door to door to get bitten by a dog. You had the ability to read those meters. It started off with AMR, where you drove by with the vehicle and did a local read, but you didn't have to go physically up to the meter and write down numbers. AMI promises not only that without the truck roll, but it also promises the ability to have more time of use visibility to customer demands. But by having the AMI meters there that can communicate out to the grid, it is now a data source. So it doesn't just give you the voltage, the load reads on a 15-minute basis. It can also allow you to connect and disconnect customers when they're switching apartments. But now it can give you real-time data feed of what's going on out at the grid. It's ironic that for years, the utility has been responsible for delivering voltage between 114 and 126, but yet no one gave the grid operators visibility to what the voltage was at the consumer's house. With smart meters, we're now getting that visibility out to the edge of the grid, and it's telling us a lot of things that we didn't know in the past. But it also gives us the ability to control things that we can control accurately in the past.
And I think just for our listeners, because I've been getting some feedback and questions, and I'm the grid lady. That's what I've been. But so we have some people that are listening, and when we say voltage or we say regulators, capacitors, sometimes that goes over our audience's head. So just from a perspective, and then I think it leads into our third question. When you think about how the power grid was designed 140 years ago, it was fundamental to Ohm's law, which is voltage equals current times resistance. So just to kind of like ground everyone, voltage is the pressure of which the free electrons move. The current is the speed at which those electrons move through the grid that we have designed for them. And then resistance is really, you can think about it like a hose where you have a faucet that turns on or kink the hose. It's resists. You're not supposed to use the word to define the actual word, but you know what I mean. The flow of the current. So it's really that beautiful mathematical equation that we have designed this very complex power grid. Now, we're not going to talk about imaginary power and real power, but a caveat to us deploying synchronous generators that spin, really we get into some complex math, sinusoid, cosine, etc. But that gives us degrees that which voltage and current operate on. AKA comes the capacitors and the regulators help move that phase angle. That's probably very high level for a lot of our engineer nerds, but just from the perspective is that we have tools in our toolbox from 100 years ago that allow us to manipulate the voltage up, down based on the distance it goes. So distribution circuits, it would leave the substation, we'd see the voltage, it'd be strong, and we did our beautiful mathematical equations that says we could take it X miles out and still have a healthy voltage at the end. And that's what you're saying, Steve, is fundamentally, the utility were required to ensure the voltage stays within this range, but we were not given any tools or sensoring or measuring or data to actually ensure that our customers are getting that. And so what the smart meters have done is given us that invaluable information that was not available before smart meter rollout. And so that's just one simple example, right? So when we talk about, the power of AMI and then the impacts of DER, voltage management becomes a very exciting topic for us utility nerds. In this case, what is that? And how does the DER and the grid edge interact with each other?
To me, what's really interesting is we've, as planning engineers over the years, we have built models and we have calculated what that voltage drop should be based off of Ohm's law and where we had regulators, where we had capacitors. And what's really interesting is with the AMI data feed is we're finding that there was a lot of information that wasn't in our models. We've got one co-op that we've worked with where the low voltage point on the entire circuit was within about 100 yards of the substation because they had high resistance that you were talking about, but the resistance was in the secondary conductor. And so they had massive voltage drop right there on the small conductors that go from the transformer to the house that was way outperforming or out detrimenting the circuit from what was seen on the primary. So the AMI data is giving us a lot of information that we had to guess at previously. And what we're finding is some of our guesses were wrong.
And I guess just to give credit for the amazing grid that we do have, and especially when it was built, we didn't have the equipment to measure the true capability, aka the true ratings. So we were very conservative in the original designs of our transformers, our conductors, and all the machines that allow electrons to flow.
And you're
So
right, we were conservative. And part of how we were conservative is we knew there would be voltage drop out there on the grid. So when we sent it out from the substations, we tended to send it out up closer to the 126 end. We'd send it out around 124 or 125, knowing that it would drop and running some calculations, but also hoping that it wouldn't drop below 114 because we didn't have the feedback. That is actually one of the real challenges that we face now, that if a customer puts in a solar panel and they have their inverter and they are providing energy onto the grid, which was not in the original design, they provide a voltage boost by putting power in out on the grid. And if they were already being provided voltage up around 124 or 125, that power boost that they pump into the grid can pump their local voltages up closer to 130, and that can cause the inverter to trip offline. So that is one of the benefits we see of trying to run the voltages lower, knowing what's going on within the ANSI voltage band of 114 to 126, is if you can run the customers lower, then when they inject power onto the grid, they don't end up with the local high voltage that causes their inverter to trip off. And that's a really bad situation. If you're the homeowner and you've invested in solar and an inverter and you're counting on pumping power just for your own use or back onto the grid and your inverter trips offline, that takes a big investment on your part and renders it useless several hours a day when you're trying to do that.
Right, and I just kind of bringing around, to our audience members, there's a lot of talk, the customer wants to now do something different than what the original design was created for. When we say the customer invested in personal assets such as solar to push the electrons, that's the first aha, right? They're now actually pushing electrons onto the grid versus taking from the grid. So that's a difference, which is change. And so the expectation of the customer and the utility and what that partnership looks like is like one of the key passion points for me, is why the electric utility that is very aware of the performance of the assets that exist should be very vocal to educate and drive the awareness so that the conversation could happen with the partnership. Because if, the cul-de-sac effect, or, keeping up with the Joneses effect, here's the grid that's been there forever. And then what do you see happen when, say, one home has solar, all the friends start installing? Well, there should be, how can we create this synergy? And so what you're saying is, with the data and the tools and the awareness, we could actually use them to an advantage of the grid performance instead of the typical response of the detriment. And then you throw batteries in there, and it becomes a whole different story. Maybe just, because I think we're getting in the weeds, but I definitely, I think it's meaty for some of our listeners, is, walk us through the different voltage applications. Like, we're very acronym heavy in this industry. So I know we're going to walk through a few, but, make sure we spell them out. But for instance, conservation voltage reduction, I think we throw around CVR within our world, but let's explain that to our audience.
We talked about the fact that you now have visibility into what the voltages are actually doing out there on the grid, now that you have the smart meters. With that information, you can now make more informed choices about how you set the voltage on your grid. So CVR, conservation voltage reduction, is a way of saying, I want to save energy. A neat idea is that your refrigerator, if you look at it, it's rated for about 110 volts. It can handle 120 volts, it can handle 125 volts. But when you run the voltage high or hot, you're actually putting a little higher voltage on your refrigerator compressor than it is ideally designed for, and it runs a little hotter. And I joke around that who wants to pay for the refrigerator to make the room hot? So by running the voltages down closer to 114, there's this term called CVR factor, which relates, as you reduce voltage 1%, you actually reduce energy consumption in the home by somewhere around 0.8% or 1%. That CVR factor is that translation between the two. And so what we found is that a number of utilities have signed up for energy efficiency programs. And one of the most powerful energy efficiency programs is simply measuring, monitoring, and controlling the voltage on the grid a little closer to the 114 side instead of up around 125 or 126. And that can save the consumer's energy. So it's on 24/7. The benefit to that for the solar panel is that if you're at a home that it used to run up around 123 or 122, and you're now down around 115 or 116, when your solar kicks in and your inverter is pumping electrons back onto the grid, and you raise the voltage, you raise it up to 122 or 123, not up close to 130, and so your inverter stays online.
So how about demand voltage reduction?
There you go. So demand voltage reduction, DVR, because we're clever with our acronyms, we use a lot of them. DVR is simply the same idea as CVR, except for instead of running it 24/7, you've got a number of utility or grid operators that really have a huge price penalty at peak. And so they can turn this technology on aggressively for a few hours each month during peak times and really cash in on the idea that they don't have to pay for those bad peak prices, and they can reduce that energy in a very targeted, focused way.
And just to kind of ground that example, like that would be a utility creating a program where they incentivize or bring just customer awareness that they can install a smart thermostat or a smart water heater, right? And they could send signals and or opt in, opt out. I mean, there's lots of ways to kind of gain customer engagement. But what that could do is there's as you said, a demand for energy. So there's a day ahead market where our transmission energy market literally says, using numbers that are not reasonable, but tomorrow we're going to have 1,000 megawatts. Which generators will be available for that predicted load? And if it's maybe a high load and there's like an extra cost for that extra peak demand, the utility could save a customer, depending on the regulation and where they are and how they sit in their business model. You could send a signal the next day to make sure you don't hit a certain level. And then the smart thermostats that all the customers have joined previously will respond by like maybe a 1 degree drop. And that could produce enough to say a 25 megawatt, drop. We've seen that. Like it's been done and proven in the industry. And so I think it's really powerful because not a whole lot of homeowners will notice a 1 degree drop. And if anything, it's saving them money. So like I think another powerful thing about educating and creating inertia around, if we have the technology and we have the solutions such as you described, which we do, and we gain that customer and the regulatory body's awareness that we can increase the way that humans use energies, awareness, to like save money, like we should be unstoppable. But I think it's really challenging, right, to really educate our customers. Because then the last acronym you have emergency, which is kind of plays into that, right? Emergency voltage reduction, which is the next layer.
So even for demand voltage reduction, that's something that the co-op or utility can do, and especially for co-ops that pass their cost on to the customers, they can do that demand voltage reduction based off their utility grid, and they can do that in addition to the thermostat control. Yep. So it's a situation where you don't necessarily have to have the customer engaged in the decision making. That's something where you can just run your grid more efficiently, and it saves money inside the home. But that's a great segue into the EVR, which is the emergency voltage reduction. And this is a situation that could happen with just minutes of advance notice, where you are counting on a certain generator to come online, and because of the severe weather, it's frozen up, and that generator can't come online. And you've got an impending crisis getting ready to happen. Through the voltage reduction tool, you can have insight to say, how much voltage reduction bandwidth do I have if I'm willing to go into an emergency operating mode, and see how much voltage reduction is available substation by substation, circuit by circuit, and say, okay, I need 100 megawatts, 200 megawatts across my system. And at the push of a button, it can do an accurate direct voltage reduction at the individual substations and buy you your 100 or 200 megawatts, which could reduce or eliminate the need to have rotating blackouts. And rotating blackouts are a nightmare. So
Right.
being able to reduce that load and still keep the lights on is a win-win for everybody.
Yeah, I was gonna say I guess 2 summers ago, California had that moment. They knew they were coming upon extreme heat, and so they started preparing their customers with communication. And so it wasn't even automated or, done behind the scenes. It was a request. Like, let's conserve some energy, and they sent out text messages across the state, and they were able to reduce it by 2,500 megawatts, which is literally a load that is like a 300,000 residential city. I mean, that's a lot of power that was able to be reduced by that emergency voltage reduction. And just for our listeners, so like to be able to have that tool, smart meters is a basic infrastructure that must be enabled.
It's probably the best way to do it. And part of why I say smart meters are the best way to do it is they give you an insight across your entire grid. So this co-op I was talking about earlier, if they installed voltage sensors, they would have put voltage sensors at the end of the line, but that's not where they had the low voltage problem on their circuit. So by having the AMI, it takes the guesswork or the modeling out of it and gives you an actual measurement of what the voltage is doing. And that lets you be a whole lot more safe and targeted and aggressive with your voltage reduction when you need to do it.
Right. And that's kind of like, we've really planned and operated the grid from a top-down approach. And so now having that data and that information at the edge is almost like a bottoms-up approach. And that gives you more information to make more granular changes. Okay. But there are options in between for those that are maturing towards advanced meters, but it's not as granular. Got it. So, how is the new age of this voltage reduction, that really helps bring this dynamic DER, distributed energy resources. And just, I think we said at the beginning, but that could look like charging infrastructure, which now is becoming vehicle to grid. So there's an opportunity for mobile charging, discharging. That is kind of a two-way street. There's solar, which is intermittent. It's not dispatchable injection of electrons. And then you have the demand programs that we just spoke about, your energy efficiency or your demand response programs through smart appliances, smart devices within the buildings, and I guess batteries. So just an injection during various times. And batteries in themselves have many use cases. So how does having these tools that you can manage voltage in the ways that we're speaking of really enable DER to kind of be brought online more rapidly, in your opinion? From your experience?
I think it's a critical enabler of those technologies. You could simply have the voltage run lower, which would help you for the solar injection, but it could hurt you if you suddenly had batteries start charging or EVs start charging. You can go beyond measuring where your low voltage points are on the grid and also measure the high voltage points on your grid. And you can balance that to give the most room to either have loads suddenly come on or suddenly go off, or generation sources suddenly come on. And so you can balance it there. I see a future where it's tightly integrated with DERMS to where you can be looking ahead. And the traditional grid voltage regulation with capacitors and regulators, et cetera, they were all designed in a different day where it was a slow and steady load grew through the day and it dropped off through the day. It wasn't a sudden fluctuation. With DERMS, we're going to need to know DERMS, distributed energy resource management.
Caught yourself.
We're going to need to know when loads suddenly are coming on or suddenly dropping off so that we've got enough generation capacity to serve the need. So if you know that 2 hours from now, a cloud bank is going to move in, or an hour from now, the fog is going to lift and the sun's going to come out brightly, you can proactively hedge the voltage on your grid, high or low, to give you maximum sustainability against the movement in the voltage that comes when those sources come on and drop offline. So it really does make a big difference in your ability to manage your grid proactively in anticipation of what's going to happen. Eventually, we'll get to where we have more smart inverter control, where they can help manage the voltage much more real time than the traditional voltage control on the grid.
Right. And I think, a common theme of grid modernization, the Grid Mod Pod, is really truly having full situational awareness to the edge. So we are an industry that have been evolving just for a short 140 years. And we built out the grid, and transmission went first, right? We networked it. It has two-way power flow. It's very complex. You have voltage, and the stability thereof is the cornerstone of the electric power grid. And so I think you said it like within minutes, you can make a change. So like on our bulk transmission system, like for instance, the 2003 Northeast blackout that took out, a big portion of our Northeast area, that was within minutes, if not seconds, that because of the reactionary time and information that wasn't being provided to the operators, it created that cascading blackout. And so when we think about the distribution grid, they're really two different beasts. However, they're evolving in the same way. We're starting to network it. It's starting to be able to change load blocks and customers to different assets. So we've kind of seen the change before. It's still fundamentally different, but it can beautifully be done. And I think I love to share if we have the data and we can take out the guesswork, build the models, run the analytics, we can start creating very fruitful solutions for not only the utility to continue to perform, but for users of energy to embrace all the new technologies. So I guess I'll just throw it over to you. Like from your history and being in the industry, what's like a lessons learned or something for a utility that's looking at this change and really starting to just crawl? Because there's definitely utilities that are running into embracing DER integration because various reasons. And then there's other utilities that really haven't seen the need. So what are some lessons to those that are just embarking on this journey that we've been talking about?
What I find interesting is just dealing with utilities across North America is some of the places that are really seeing a surge now. 5 years ago, I would not have expected the surge, nor did they. And so what we're seeing is this is a universal consumer level interest in the solar. We're seeing it in the Northeast, not just in California. We're seeing it in the middle of the United States, up in Canada. So I think really change management starts with realizing that you're probably not going to be insulated from this. This is something that is coming. It's coming in a big way. It's getting a lot of regulatory support. Look at your distribution grid, look at your transmission grid, and start thinking about what it means to you. The other element is there's great opportunities for industry consortium to look at this and say someone else has solved this problem and they solved it in the last 5 to 10 years. Build those relationships, build those networks, human networks, not electrical networks, and learn from those who've solved it first.
For all of my peers that are listening, I've been making a joke that I find that I didn't really understand the power of change management, organizational change management. And I actually feel that maybe that's where my true passion lies. So the fact that you bring it up on this episode is just beautiful synergy. Well, Steve, thank you for the fascinating conversation. Voltage is such a fascinating variable topic, importance for the overall grid's performance. So hopefully our audience gained some valuable insights of the challenges, but also the solutions. And I think that's key at the intersection of embarking and embracing this new technology, distributed energy resources, and grid management. So really tapping into that the grid operators are what they're going through to really help us create a more resilient and energy efficient system with these tools that you've described. So thank you for sharing your knowledge to our listeners. We'll wrap it up here.
That's a wrap for this week's episode of the Grid Mod Pod. Thanks for tuning in. We hope today's conversation got you thinking about new and creative ways to improve our power grid. Be sure to subscribe to our YouTube channel to be the first to hear new episodes. This podcast is brought to you by AEIC, the place where operations leaders come together to share knowledge and provide guidance to the electric utility industry. We'll be back with a new episode soon. Until then, keep powering on.